Okay, financial lit, we covered how to solve for time. And the two instances in this unit that we're going to solve for time is when we're going to be talking about simple interest, but we already know how to do that. We did that with division. We isolated the unknown with simple interest and we solved for it. And we've done that. I think that's the only time we've done it. So now we're going to do it with compound interest and continuously compounded interest. So when we're talking about that, we need to use a logarithmic equation because they help us. A logarithmic equation always equals an exponent. And that's going to help us because they will undo exponents. So they're the inverse exponents. They're the inverse of an exponent. We are going to use common log or base 10, log base 10 for all of the compound interest problems. Sorry, I'm going to repeat. Okay, so we're going to use those for the compound interest. And the reason why we're going to do that is so we don't have to worry about remembering how to do change of base or any of that stuff that we learned in functions. This will help us just take the same base on both sides. We can still apply those logarithmic rules that we learned, that if we take the log of this and this, that means the exponent will be multiplied by that log, and we can still use that idea. Another thing that we're going to use is natural log, and we use natural log a little bit in functions, and I think you used it in honors algebra too, but I'm not 100% sure. But I know for sure in functions we used it, and when we see natural log, which is I write it like this. Sometimes it's on your calculator, it's a capital N, capital L, or it can be just written as lowercase l, lowercase n. They all mean the same thing, it's just different forms of saying it. And we're going to use natural log because natural log is log base e, and if we're going to use it, it'll help us with our continuously compounded where we see another e. So we have some rules that come with that, but we're going to talk a little bit about that. So we're going to use natural log and we're going to use common log. Now, these things are on our calculators. Let me see if I can. So if we're using our TI-83, the log button is right here by the 7, or right below the x squared next to the 7, and the natural log is right below it. So we've got log, natural log. Remember our e is going to be second in the division sign. If we want to take e to a power, we can do second natural log right here. That'll work. You'll see the little blue e to the x, and then we can put that in for our p e, or b equals p e to the rt. So we can use that, but I just wanted to show it on the calculator so you know where to find it. Also, you can type log or ln when you're using Desmos. So one of the big things that we want is we know that we can take an exponential, which is this. This is also an exponential. This says a base, this says that a base raised to a power equals an amount. This says that our amount is equal to a base. This whole thing is going to be our base. Raised to this power is going to be that. The same thing says here. A base, these two things multiplied makes a base. Raised to a power is equal to an amount. So those things are still the same thing. This is an exponential, this is an exponential. So this is an exponential that we're a little bit more comfortable with seeing. This is a log that we've seen before that says this base to this power equals that amount. So we've got a logarithm equation always equals an exponent. So what we want to do is we always want to get our form to be one number equal to another number raised to a power. So that's what we're going to do. So a lot of times what we can do is we can get rid of our principal right away when we're solving so that we can just get this number by itself to kind of make it just a little bit easier. So that is what we are going to do. So our first example, I'm only going to do a couple examples on this video. If you need more help from me, you can always come see me, but I'm only going to do a couple examples. So we are going to do example number 1, which is Nancy and Bob. And they want to renovate their kitchen. So I'll give you a minute to read this and then we'll talk about it. Okay, so we have this. We are talking about something that is that compounds interest monthly. So that means I am going to be using this compound interest formula because I'm going to have an n. So I'm going to go ahead and plug in the things that I know. So I know my principal is $16,000. I know that my rate is 0.024. I got that right there. I know that my time, I do not know my time. That's what we're looking for. That's the how long. And I know my n, the number of times compounded, is monthly, so that's going to be 12. And I know my ending balance. My ending balance, what I want to end up was 20,000. So what I'm going to do is I'm going to go ahead and plug all of that in. I'm going to plug it into this formula right here. So I know my B, my P, my R, my N, and my N. So we know both those numbers. So I'm going to go ahead and plug that in. So I know that it's going to be 20,000 because that's my B. It's going to be times 16,000 times 1 plus my R, 0.024, divided by my N. And I'm going to raise all of that to my 12 times my time. And I'm going to just put T for time because I don't know what it is. And I just want to use a number. So one of the things that I said is we want to get it down to one base, right here. Nope, right here, sorry. We want to get it down to one base to a power is equal to a number. We don't know what this power is. So since we don't know what this power is, we need to do that. So PEMDAS tells us that we can do parentheses first, and we actually can add 1 plus 0.024 divided by 12. We can figure out what that is. So we're going to end up with 20,000 is equal to 16,000. And that's going to be 1.002 raised to the 12t. I think that's what it is. I didn't check my calculator. Yeah, that's what it is. Okay, so now we have this number raised to this power. So what we want to do is we want to get this whole thing by itself. So to do that, we're going to divide by 16,000, because that's how you get it away. This turns into a 1. But if we do that over here, we're going to end up with 1.25 is equal to 1.002, still raised to the 12t. Okay, so we know some rules about log, that if I take the log of this, I can move this exponent out front. So what I'm going to do is if I take the log of one side, I need to take the same exact log of the other side. So what I'm going to do, and we already talked about how we are going to use this common log, so I am going to take the log, I'm going to write my word right here, I'm going to take the log of this side, 1.25, and it's going to be equal to log of 1.002. And then that means that this 12t now comes down since I took the side. I know that I'm going to be multiplying by this 12t. So now I'm getting closer to what I want, where I want a base. So now I've gotten here, but I have too many things going on. Like I have a log, I have like being multiplied over here. Like I have a lot going on. So to get it all the way away from that, I want to get this 12t all by itself because eventually I want to solve for t. So what I'm going to do is I'm going to divide both sides by log of 1.002, and I'm going to divide by log of 1.002 on both sides, and I'm going to end up with 111.683, we'll say. We'll just round to there. So now I know that that's equal to, the only thing that's left, because this turns into a 1, is 12t. Well, how do I get 12t? How do I get the t away by itself when it's a 12t? I divide both sides by 12. I end up with t is equal to 9.31. And so that tells me that it's going to take this account 9.31 years to get to that 20,000. If I start with 16,000 and I use that 2.4% for compounded monthly. So that's what that means. So now we're going to do an example of natural log. And we'll go ahead and do example number 6. So if you go to your notes and go to example number 6. So we are going to do the same thing. So go ahead and hit pause and read the problem. And then we're going to punch in the things that we know. So we have our formula right here that we're using because it's compounded continuously. It says it so right here. Compounded continuously. So I'm going to say P is equal to 9,000. And then I have my R is equal to 0.043. My T, I don't know what that is. I'm still figuring that out. And E equals E. So now this one actually has less steps and is a little bit more fun. So what we're going to do is we're going to apply, oh, and my ending balance. Sorry, I forgot that. My B is equal to 100,000. So what I'm going to do is plug in the things I know. So I have 100,000. 100,000 is equal to 9,000. And then it's going to be times E to the 0.043 times T. So I've got that. So what I want to do is I want to get this whole thing by itself because it's an unknown and I want to get it by itself. So I'm going to divide both sides by 9,000. And I get 11. 11 is equal to E to the 0.043t. Now the other thing I said was I want to take the natural log of both sides. But natural log is log base E, and if I take that equals natural log. Those things equal each other. So if I take, I'm going to write it up here. So if I take log base E of E, if we remember from algebra 2 functions or wherever we learned logs, we learned that these two things turns into a 1. So if I take the natural log of both sides, this turns into a big 1. And this still comes down just like it would if I were taking the log. So then I end up with natural log of, oops, I wrote the equal sign, sorry about that. 11.11 is equal to 0.043 times t. Well, we know how to solve something like that. This is just a number. It looks funny because it's got the natural log, but we're just going to divide both sides by 0.043. This turns into a 1, divide 0.043, and we end up with t is equal to 55.996, and I would say here we're going to round to the nearest whole year because it's pretty close. So t is equal to 56 years. I've got this. Okay? So if you have any questions on that, please ask. I will see you all when we get back. I will have those worksheets and we'll have time to work on that and we'll have a review after this. So I hope you all have a great day and I will see you later. Thank you.